Okay, so this video is going to just kind of go over a few of the problems in this chemical reaction rate 1 lab activity that we have here. This will be a paper lab, so there's no chemicals, nothing like that. We're just going to be working reaction rate problems. So I wanted to go through a couple of them, and I also wanted to just put your mind at ease a little bit. This is a 12-page document, but the first 6 pages are basically just notes, just something for you to refer back to when you're actually working out the problems. So we have what the rate equation is. It's the change in concentration over change in time. We have a lot of terms for you, vocabulary words for you. So as they're asking questions, you can go back and refer back to these terms. Hopefully that you have already watched the 2 ed puzzles on reaction rates, especially the first one, introducing reaction rates and instantaneous rates and that kind of thing. And then also we have the differential rate law. That would be the second ed puzzle you had. So you need to make sure that you have watched those first. That'll be a big help to you. So we talk about differential rate law here. We talk about zero order, first order, and second order, and it gives you an explanation of what those are and the equations that go with those different types of reaction orders. And then they give you a couple of examples with the data from experiments and so on. So what you'll basically be doing when you're asked to do these types of problems is you will have some experimental data, and you'll have to analyze that data and choose which data points you're going to use to help you find the rate law. So where do you start? The answer is with the controls. Okay, so experiments 1, 2, and 3, you're going to hold B constant, and that's where you'll start. Okay. The rate stays the same regardless. So if you look at the data table, you'll see that the rate stays the same regardless of how the concentration of A changes. Therefore, it is zero order with respect to A. And so you'll just need to make sure that you read through and scan through this and then refer back to your notes. Okay. All right. So here are the actual procedures and purpose and procedures of the activity. And then it skips to conclusion questions. The conclusion questions are the questions that you have to answer. So there's nothing else in between there. Okay, so in the first one, we have a reaction rate between carbon and nitrogen dioxide. I believe we talked about this particular type of reaction in your notes, but anyway, was studied at 650 K, starting with various concentrations of CO and NO2. And the data in the table were collected. The reaction is shown below. So here's your balance. Here's your chemical equation. You'll need to make sure that it's balanced, and in this case it is. And here's your data table. So the first thing you have to do is write the rate law that is consistent with this data. All right, so in experiment 1 and experiment 2, the concentration of CO is held constant. So if you look here, so remember when you did the equation, when you did your notes, we talked about having to pick a couple of experiments. And so you want to pick the 2 reactants, and you want to pick 2 experiment numbers or 2 trials where one reactant is held constant, and then 2 trials where the other reactant is held constant. And you're going to use that to determine your rate law. So for the first one, in experiment 1 and experiment 2, the concentration of CO is constant, which we can see right here. And the concentration of NO2 is actually doubled. So here's your initial rate for experiment 1, experiment 2. Here's your initial concentration. The concentration is doubled. So if it doubles in response, the reaction has to be first order with respect to NO2. Okay. And then in experiment 1 and 4, the concentration of NO2 is held constant. So I'm going to change pen color so we can see. All right. So in experiment 1, NO2 is the same number. Experiment 4, NO2 is the same number. So that's going to help us determine the rate law for the second reactant. The concentration of CO2 in those two experiments is also doubled. 0.51 times 2 is 1.02. Okay, so since that is also doubled, that means that it also is a first order with respect to the CO. So our rate law then is going to be some constant K times the concentration of CO times the concentration of NO2. And that's your answer. Okay, so the way we got that, and as far as showing your work, because on here I did say you need to make sure you show your work. What you will need to show me is that for experiment 1 and 4, the NO2 is constant and the concentration of the CO2 is doubled. Okay, and for experiments 1 and 2, the concentration of CO is held constant and the concentration of the NO2 is doubled. Okay. And so that means if the concentration is doubled, then that means that it is first order for that particular reactant. Okay. Zero order, if you go back up and look at your definitions, you'll see that. Let's see, where's our... All right, so right here, zero order means that there's no effect on the rate at all. First order means it's directly proportional to the concentration. So doubling the reaction rate doubles the rate. And that makes it first order. Okay. Second order would be if the concentration gets doubled, then the rate is quadrupled. Okay. So that's where I got that information from. So if we go back to our table, here we go. All right. So rate increases by 2. That's a direct relationship. So that means that's first order. Question B, calculate the value of the specific rate constant K. All right, so to do that, what we're going to do is just rearrange that rate law for K. All right, so algebraically, we're just going to take K and solve it, get it by itself. So we're going to have rate over the concentration of CO times the concentration of NO2. And then what we're going to do is we're just going to take numbers from an experimental trial, just pick one, it doesn't matter which one, and take those numbers and put into that equation. So if we want to, we can use the first one. We can use experiment 1. And if we use experiment 1, that's going to be 3.4 times 10 to the negative 4. And then we need to put here moles per liter hour. And then we're going to divide that by our concentrations, which would be 0.51 moles per liter times 0.035 moles per liter. Okay. And that means that moles per liter will cancel with this moles per liter, and you'll be left with moles per liter per hour. So I'm going to let y'all work out the math on that. The unit for that is going to wind up being moles per liter, or molarity to the -1, hours to the -1. Okay, those will be your units. But you yourself need to work out and get the number answer. I'm not going to do any more of this problem for you than I already have. Okay. All right. So on C, what is the overall order for the reaction? All right. To get the overall order, all you're going to do is add up the exponents for the concentrations in the rate law. So if we go back to the rate law, come on. If we go back to the rate law, we can see that our concentrations here basically have an exponent of 1. If there's nothing written there, that means it's a 1. Okay, so 1 for this one, 1 for this one, that's 2. So it's an overall second order rate law. And again, you have to show your work on that. So to show your work on that, you would just add the exponents for each concentration for each reactant. All right, question number 2. I'm not going to do every single one of these, but I am going to kind of get us started so that you know what to do, what to look for. The initial rate of the reaction of nitrogen monoxide and oxygen was measured at 35 degrees Celsius for various initial concentrations of NO and O2. The balanced reaction is shown below. Okay, so you got the reaction, got your data table. We have to write a rate law that is consistent with this data. So again, what we're going to do is look for reaction trials where one thing is held constant, and we look at the change in the other reactant. And then we look for reactions where the other reactant is held constant, and we look for changes in the first reactant. Okay. All right. So what we're going to look at first is we're going to look at experiment 1 and 2 again, because we notice in experiment 1 and 2, our oxygen concentration is held constant. And our initial concentrations of NO are doubled. We go from 0.02 to 0.04. So we can see that those double. So as one goes up, the other goes up. They both in both experiments, they go up. So that means it's going to be first order with respect to the NO concentration. And then we're going to look at experiments 2 and 4 for our second one. So in 2 and 4, we see that the NO concentration is held constant, and we see that the concentration of O2 is doubled. No. Is that correct? Yes, that's correct.